Okay, we start our discussions of convex functions. So we have discussed convex sets. So we are going to discuss convex functions and its implications in optimization. We will also speak about very basic facts about optimization, but link it largely with convexity because I think that is what will be there in your syllabus. Convex functions will play a major role. So a convex function is defined in the following way, that if you have a subset C of Rn which is a convex set, then a function is said to be convex if this inequality holds for all x, y in C and any lambda between 0 and 1. Of course, you know this is well defined because lambda y plus 1 minus lambda x is in C because C is convex. So this is a well defined, this is a very well defined functional value, and so this is a very well defined thing. So you know these functions look like this. A convex function would usually look like this. A best way to recognize a convex function is the following. If you have a function say from R to R and you want to recognize whether it is convex, you take the convex function and shade the upper part of the graph, shade the region above the graph. This region above the graph is called the epigraph. And if the epigraph forms a convex set, then the function is convex. And if the function is convex, the epigraph must be a convex set. So this is a very, very important thing. I'll ask you to prove in the, I'll ask you to analyze this in the tutorial class. But so now let us see certain examples of convex functions. So let us consider the case when C is equal to R. That is, the whole real line is the domain, right? So here we have considered f from C to R, where C is a convex set. Now here C is the whole real line R itself. So fx equal to x, fx equal to mod x to the power p. So these are, so for example mod x, this function is a typical, very typical example in any convex analysis book, absolute value of x. And you will observe that the minimizer of this function is at x equal to 0, and at x equal to 0 the function loses differentiability. So the standard technique of f dash x equal to 0 of finding an optimizer or finding a minimizer doesn't really work in this case. Okay. So here are some other domains where C is R++. R++ means the set of all x in R. This means the set of all x in R such that x is strictly bigger than 0. They are positive numbers only. Otherwise log cannot be defined. Fx is equal to log x is not, fx, if I just put log x, then it is not convex. But the negative of log x is convex. This function also turns out to be convex. Okay. Convex function and its basic properties. We are not going to push in too many properties because that will just confuse you at the very first leg. So there are many, many examples of convex functions, many, many intricate and many, many interesting examples of convex functions, but we are not going to give all those examples here because those can be mathematically very demanding in certain cases. So we will not do them. We will do the ones which are well known and very standard basically, and used also in real, actual real applications. So now consider the case when x is in Rn, not just in R, then first take the case where domain is the whole space Rn. So fx is equal to summation xi square, which is nothing but the square of the distance between any vector x and 0, right? And x1, x2, xn are the coordinates, and this is a convex function. The root of this is nothing but called norm of x. So norm of x is the distance of a vector from the origin 0. This fx is equal to sum of mod of xi, I equal to 1 to n. This is called the 1 norm or L1 norm. These are all norms. Any norm, I don't know how many of you know the definition of a norm. Norm is nothing but the distance of a vector from 0. Just keep that in mind, because there are a lot of engineering background students. I don't want to get into the mathematical intricacies of the axioms of norm and all those things. So there are distances. Basically, you can define distances in different ways. Like this distance means if I go from A to B, I go from A to C, then C to B. This distance. This is called the taxi cab metric, taxi cab distance. So this is called the L infinity norm or the max norm. So here the norm is nothing but this. So f of x is max of the modulus of the modulus of x1, modulus of x2 dot 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 xn. So you take any x, find the moduluses of all these and see what is the value. So the maximum value of all these is fx. This is actually a convex function. So there is this standard result which I don't mention here in the notes, but just I will ask you to solve it out. That suppose I take a max of say some finite number of convex functions. So where f1, f2, fk, each of them are actually convex functions. So you have to prove that fx itself is a convex function. So these mod x1, mod x2, mod xn individually are convex functions because of this. So then these are also, so hence the maximum of this family of convex functions is a convex function. Now this is a standard quadratic function. Anybody who has studied quadratic forms in linear algebra, you would remember this. This is standard quadratic function, right? This is called quadratic function. If Q, this is a Hessian matrix, you would twice differentiate it, then the Hessian matrix is Q. Then Q is positive semi-definite. By a matrix to be positive semi-definite, we mean that the following is true. So now we consider the set C, which is a subset of Rn plus plus. So we have extended what we had known. So if you have a function on this form, this is a convex function. This is actually used in information theory. It is called the negative entropy function. This is used in information theory. Its domain is Rn plus plus, means all these x1, x2, xn, they all has to be positive, otherwise you cannot operate the logarithm. Logarithm always needs positive numbers. Now this fx, if I don't take the minus, then this is a class of functions called the Cobb-Douglas functions, and they form what is called concave or quasi-concave functions used by economics. Used heavily in economics. You see that if f is convex, it implies that minus f is concave. So the that is called a negative of this function. If a convex function looks like this, a concave function would look like this. So anything which lies below the graph, if you shade it, so that would give you a that would give you a this part is called the epigraph, this part is called the hypograph. So the hypograph is a convex set, that is a concave set. Convex functions are also studied in a more general framework where apart from just having a function from C to R, we can always define a convex function whose domain is Rn itself. But we now would need to attach two values, infinity and minus infinity. So you might say, okay, infinity is not a number, why are you attaching this value? But these are largely conventional things which help us in understanding. You see, when you have a function like this and you want to define convexity, you can define convexity by the same inequality that we have used. But you have to understand when you have this form that so when you are writing the definition down for such a function, so what would happen? Suppose I have fy to be plus infinity and f of x to be minus infinity. Then how do I define the function? Because plus infinity and minus infinity. So lambda into plus infinity is plus infinity. Any normal number, if you multiply with plus infinity, the convention is to take it plus infinity. If you multiply any normal number by minus infinity, and any positive, non-negative number by minus infinity, the convention is to take minus infinity. Is multiplying a given positive number with a very, very large, small negative number. So that's. But what happens if you come to the situation now? Here, then I would have a situation of infinity minus infinity. So what is the meaning of this infinity minus infinity? Usually, it is, many people don't want to define it at all. But to define convexity of this kind of functions, we will tell you why these kind of functions are coming, why such a thing is accepted. Right? We will very shortly come to this, and it has links with optimization, of course. So that the reason why such framework is used is essentially because it has links to optimization. So what is happening is the following, that if I want to define a convexity for such functions, now again I want to re-emphasize that you don't, if you ask me now that why you have taken such a general framework where you have used infinity and minus infinity, that I will not be able to answer right now, but we will come to the framework very soon, right? Why we are doing so. So then infinity minus infinity becomes a bottleneck which many people want to avoid, but we will take this convention infinity minus infinity equal to infinity, a convention taken by Rockefeller, so that you can actually define, keep your definition intact. Because if it is infinity minus infinity is infinity, it doesn't matter what is here on this side. Minus infinity, plus infinity, or real number doesn't matter. The right side is maintained, the inequality is maintained. So this is a very important thing that I want to also emphasize to you, that many parts of mathematics, a lot of things are conventions. Because without those conventions, no logical progress can be made further from those things. So here is again the definition of an epigraph which we write formally. So epigraph of course means that you take any point here. So here is your x alpha point. So this is your x and this is your alpha. But what is f of x here? F of x is this. and this is your alpha. So naturally you see f of x is less than equal to alpha. Just have a look at this diagram once again. Basic coordinates. So that is the definition of the epigraph. So usually we tend to avoid this sort of, if you want to avoid this definition, then you have to come to this definition that if you have a function from Rn to plus infinity minus infinity, that domain, then the best way to define it is in the following way, that a function f is convex if and only if its epigraph is convex. See, definition, when I say a definition, it is always both ways. Definition is always if and only if. Okay. So this is the way to define if you want to avoid such definitions. Now once we admitted that function, you see I can always immediately put any function. For example, I can write the function fx is equal to minus the natural log of x, means log base c, when x is in R plus and is equal to plus infinity otherwise. So if I define it like this, I am done. So I have actually then the log function is now defined from Rn to R union plus infinity minus infinity. For a large part of the problems, for a large class of the problems, we talk about proper convex function. A proper convex function is a function which is defined from Rn to this whole interval minus infinity plus infinity. It means it is real line and also these 2 points, minus infinity plus infinity. So don't worry, if you want to do real good optimization, you have to get used to this handling of minus infinity and plus infinity. Not a single good book in modern optimization can escape this notational thing. You have to have it. So a function is said to be proper if the following holds. That is, if fx is strictly greater than minus infinity, that is, fx never takes the value minus infinity and it can take the value plus infinity, there exists an x in Rn for which fx is finite. So the set of all x for which fx is finite is called the domain of f. So the domain of f for this function is R plus plus. So we will give some more examples. For example, this is a simple example. Okay, what's up? So here I have taken a function fx is equal to 0, if x is equal to 0, if plus infinity is when x is not equal to 0. Let us draw this and then see what we mean by this. So I am telling it is 0 at 0 and it is plus infinity otherwise. See, when you are drawing the the epigraph only can be drawn over finite points. If fx is plus infinity, then you cannot have something like fx less than equal to lambda alpha. So here if I draw the epigraph of this function, this one. And this is the epigraph, it's straight, the positive y-axis. This is your EPF. And of course, the epigraph of f is convex. Of course, the epigraph of f is convex. The set is, it is a convex set, and hence this is a convex function. An extension of this very simple idea is the idea of the indicator of a convex set. So from just a singleton set x equal to 0, we are enlarging it to a convex set C, and so indicator function of a given convex set C in Rn says that if it is 0 if x is an element of C, and if it is plus infinity if x is not element of C. Let us see what happens. So let us just look into the situation where we are in R. In R, then it is better to understand it. So I have this is my C, for example. So then means outside C it is always plus infinity, and inside C it is 0. So what is the epigraph of this? And this is a convex set. See, this approach of looking at convexity, I can only assure you that you are at the frontier of knowledge. You are absolutely at the frontier of the subject. So you see that this is now a convex set. Now there is a problem. For example, I say that, okay, consider a function fx is equal to minus infinity when x is equal to 1 is equal to 0 when x is equal to 0 and is equal to plus infinity otherwise. এই কালকেরটাই কালকেরটা কোথায়? So suppose I define a function like this, then how would I try to draw it? So the function is defined in this particular format. Is the following, that here what it says that at 0 it is 0, at 1 it is minus infinity, means this one is here, and then it is plus infinity at other places. So if I draw the epigraph, what is the epigraph? This is the epigraph, this part is in the epigraph, and minus infinity means this whole line would be in the epigraph. So this has to come from the bottom, because the functional value is minus infinity, any real number is bigger than that. So the whole line would be there, the line vertical to the x-axis and passing through x equal to 1 and y equal to 0, of course. So that is exactly the line. So now you see the epigraph now consists of this ray and this line, and hence it cannot be convex, because if I take a point here and I take a point here, they are outside epigraph. So if you have the point minus infinity, if there is any point in the domain, the function takes the value minus infinity, then it has to take the value minus infinity throughout the domain. If any point where it takes minus infinity, so there will be certain parts which it takes plus infinity. Any point which it takes minus infinity means then it has to be minus infinity throughout, either or else the convexity of the epigraph of the function would break. It won't be a convex set. So for example, if I just, I'll tell you a bit more easier example, but it will look easier. plus infinity when x equal to minus 1, sorry, minus infinity is 0 between when x is in the open interval minus 1 plus 1 and is plus infinity otherwise. So, you look at a function like this, it says that minus 1 and plus 1, the function is infinity, minus infinity. It is 0 in between and plus infinity outside. So, the epigraph is this. The epigraph is now this and this part. Now, you see this is not a convex set because I take a point here and I take a point here, and if I join them by a line segment, part of the line segment is outside the epigraph. So, this epigraph is not a convex set. So, if it has to be minus infinity at one point, then it has to be minus infinity throughout, then only I can have an epigraph to be convex set. So, if it is minus infinity throughout minus 1 plus 1, then epigraph will become a convex set. So, that is why such functions are avoided basically. So, this is another important function called the support function of a set, but you need not bother with this at this moment, maybe sometimes. So, I have not spoken about the continuity property in the slides. I thought I will just tell a bit about the continuity property of the function. So, we are now coming to continuity and differentiability properties of functions. These are all topological properties basically. So, sorry, I think I should not use the word topology and all those things. So, these are properties which are important because continuity and differentiability are basic things that you learn in calculus. You want to know the continuity of the function, you want to know the differentiability of the function. So, these two would make a, these two would play an important role. So, let me talk about the continuity properties first here. If f Rn to R union infinity plus infinity, I am just talking about proper functions, is a proper function and interior of dom f. See, for a convex function f, the domain of f itself is always a convex set. The domain of f itself is always a convex set. Interior of dom f is equal to, if this is not equal to phi, that is, it is not non-empty, the interior. So, the dom f is full dimensional, that the affine hull of the dom f is exactly equal to Rn. So, if this happens, then f is continuous on Rn. Continuous, yeah. F is continuous on the interior of dom f. This is a fundamental theorem, the most general structure. Of course, then, so the corollary of this result is the following: f from Rn to R. So, f is a convex function from f from Rn to R be a convex function. Then f is continuous. So, this is a very important thing to remember. In fact, if you said any, instead of Rn it is any open convex set C, then also it is continuous. So, these are very important things. Then I am talking about differentiability properties. I do not know how many of you actually know about differentiability of a function. So, this is an important thing that one should learn. How many of you know about differentiability of a function? Can anyone write down the derivative first, definition of the derivative of a function of a single variable, f dash x? Can anybody write the definition? Anybody can write the definition of derivative f dash x? And do it on the board. You are right, you are not right. Anybody else? He has spoken yesterday. Anybody else can write the definition of the first derivative? Who? You want to write? Okay, fine. Solve it. So h tends to 0 means h tends to 0 from both sides, plus and minus. Solve it. So now what happens is I can write down this one, because f dash x is now a fixed number when you fix the x. I can write down this one as limit this limit is 0. You can combine, you can take f dash x to this side and put it inside the limit, that is all. You will have this expression. So when once x is fixed, this is a function of h. So I can write this, the top thing is function of h, pi h. So what we have got finally here is limit phi h by h is equal to 0 as h tends to 0. So any function phi h for such that phi h by h as h tends to 0 is 0 is called the small o of h, small order of h, which means that phi h goes to 0 faster than h. Because if h goes to 0 faster than phi h, then obviously this value, this is actually increasing then. So in order to have this going to 0, phi h must go to 0 faster than h, and phi h is called a small o of h quantity. And so the derivative can be now thought of as a real number which satisfies this. From here, this is phi h, this is equal to phi h. So f of x plus f dash x h plus small o of h. This is nothing but the Lagrange mean value theorem, that's all. How many of you remember the Lagrange mean value theorem taught to you in calculus? Some vague idea. Anybody? How many of you have done math in your engineering courses? All of you, I am sure. So this is the Lagrange mean value theorem. That's it. Okay, so now, so when you come to higher dimensions, you know that this multiplication will be changed by inner product. So for a higher dimension, the definition of the derivative is following. So the function f of x plus h, that is given a function at x, value at x, the value at points away from x can be evaluated. So what does this mean? This actually tells you that when h is very small, I can approximate the value of f of x plus h by using this value. So which means at the point, so if you have a function, any function like this, so at x, if I move very little away from x, so this is your x and I move very little away from x, then I can actually use the value of my tangent as an approximation to the value of the curve. So the tangent can approximate the curve, that is, this is so small that the curve would appear like a straight line, that the tangent would now actually approximate the curve. So this is a well-known technique in the sciences. It is called the linearization technique. It's used in many places in many ways. So I can now, and I want to repeat this writing. So it is now, so there exists some vector v. So our derivative is a vector v, which satisfies this. So instead of this multiplication, I change it by inner product and this error term, that is okay. This difference is not exactly equal to f dash xh, but there is some error. That is why in the Lagrange mean value theorem you write that this is equal to f dash xi, where xi is some number lying between x and x plus h. So that is actually captured through this. And so instead of h now, because h has now become a vector, because your x is in Rn, so if you move from x to some other point x plus h, now this h is now a vector, it is not a real number anymore, right? So I have to write the following. So this is what a derivative is, definition of derivative, and if you actually compute it out, it is nothing but the following vector, which consists of the partial derivatives of f, and this is nothing but the grad of f at x, which is a standard symbol, all engineers know this. So if a convex function is differentiable, then if a convex function is differentiable, then it follows the following property, then it satisfies the following property. And if there is any, that is for any xy in the open convex set C, this property has to be satisfied. See, whenever you are talking about differentiability, either you have to talk over whole Rn or you have to talk about over open set. Because if you just take a closed set, there can be problems at the boundary. You can define continuity at the boundary, but derivatives cannot be defined at the boundary, because derivative must capture local information. If you are not going outside the boundary, it cannot, they don't give you any local information. You need local information around even the boundary point. So if you want to have local information around the boundary point, you will have to go outside the domain, and outside the domain the function may not be defined. So at the boundaries there is a lot of problem. So if you have an open convex set, or not a convex set, though, because I am defining convex function, so it is convex set. So for an open set, there is no boundary. And so you can always, this is an interesting thing, that open sets do not have boundary, so you can always, given any point, you always have a neighborhood around which you can have local information. That is, you can compute the functional values. So derivative is a very local thing, so that has to be kept in mind. We need local information about the function. So our function f, a differentiable function f is convex if and only if the following holds for every x, y and c. Now if you observe that if I get an x bar, if I fix an x bar and such that grad of fx bar is 0, then fixing that x bar, we can keep on changing the y. And then that would lead to the fact that if grad fx bar is 0, then fi would become bigger than fx bar. Because if this expression in this expression this is true for any x, y in C, or Rn if you want to say. So what would happen if I fix an x and keep on changing the y? The relation is also true at that time. Suppose I have an x bar such that grad fx bar is 0. So which means I can put grad fx bar equal to 0 here, and I fix the x bar and keep on changing the y's. So fy minus fx bar is greater than equal to grad of fx bar y minus x bar for all y in C. C bar or Rn, what you want to mean. So whenever grad fx bar is equal to 0, so if grad fx bar equal to 0, it would imply that f of y is greater than equal to f of x bar. That's it. So x bar becomes a global minimizer. In fact, a very general result is that if you want to minimize a function, convex function over a convex set, every local minimizer is global. There is no local minimizer. So I would like you to, in the gap that you have now after the class, to figure out the definition of a local minimizer and a global minimizer and their difference. So in the next class when we start, somebody has to tell me what is a local minimizer and what is a global minimizer. You use the internet or whatever you want. So the optimality criteria which I had just spoken about is the following. So if C is equal to Rn, this is the optimality criteria. And if C is open, like what we have just done, then this is the optimality criteria. So the general result is that, the following. Every local minimizer of a convex function over a convex set C is a global minimizer. So convex functions are important in optimization because we don't have to get locked in local minimizers. We all have global minimizers. So I sure you know that you have learned some basic calculus that okay, this is a local minimizer, but then this is a global minimizer. Like if you have a function like this, so you know that this is a local minimizer, this is a local minimizer, but this is the global minimizer. But a convex function does not have a local minimizer. It always has a global minimizer. And that is why it is important in optimization. In optimization, we are seeking to minimize a function. When I am talking about minimizing a function, I am always talking about global minimization. But what happens is that in most practical situations, when the functions are bizarre or non-convex, we just do not have any chance of finding a global minima. It's very difficult. So then we really have to keep ourselves happy with the notion of local minimizer. So, but the beauty is that for a convex function, we don't have to bother about it. Every local minimizer is a global minimizer. So this is a very important thing. Once you do anything in optimization, whether you use it in your thesis or use it as a particular, some application you're just trying to apply the techniques in your actual work, please remember that this fact that for a convex function, if you want to minimize a convex function over a convex set, then every local minimizer is global, is absolutely fundamental to the understanding of optimization itself. Next comes into much more important issues. We have earlier considered differentiable convex functions, but are all convex functions differentiable? For example, we had drawn this function fx is equal to mod of x, the absolute value of x, and we have shown that it need not be differentiable. In fact, if you look at it, the differentiability, non-differentiability comes exactly at the point where it has the global minimizer. So that is why you have to devise techniques other than f dash x equal to 0 to really speak about the minimizer, if you want to find a minimizer. In fact, what it shows is that there must be some tool which has to replace the derivative. In order to find the minimizer, we need some derivative like tool, but it cannot be the derivative in this case. The derivative doesn't exist here, right? So what we say here is the following, that A convex function is differentiable almost everywhere. Mathematicians would realize that I mean that the set of points where the convex function is not differentiable forms a set of Lebesgue measures 0. But I do not want to bring in measure concepts here because everybody might not be well versed with that. What I want to say is that it means in general except a few points a convex function is differentiable at all other points. Here you see just except that one point the convex function is differentiable at all other points. The derivative on this side is plus 1 and derivative on that side is minus 1. So you see what I have just exactly this is what I have told you. But you see non-differentiability in convex function doesn't appear out of the blue. It appears in a very ordered fashion. It largely appears for functions of this form, the max function. Generally non-differentiable means that in general they are most of their all functions largely except a few pathological examples all functions of this class are not differentiable everywhere. So because here if all these are convex, this function is also convex. That you will prove in the second half and in the tutorial class. This is a very important exercise to understand. I will tell you why it is an important exercise because it will link you up with the exercise in or the properties of convex sets that you have learnt in the last class. So you see if you look at the function fx is equal to mod x, this function. You know I can write this in another way. This function can be written as fx is equal to max of x and minus x. Why? Because you see what is your x? Y equal to x. This is the equation of y equal to x. What is the equation of y equal to minus x? This is the equation of y equal to minus x. So when you are coming from this side, the negative side, you see y equal to minus x is bigger than y equal to x. So this part is there in the function. At x equal to 0, both are having the same value, 0. But once I come to the non-negative side, the x, this part, the x is bigger than minus x. So you see the absolute value function is nothing but f of x and max of f of x and minus x. So the non-differentiability largely arises where an operation of max function is going on. This is absolutely a real fact in convex optimization. And what happens is the following. You observe that the differentiability is, now you see, here I put, say I put x equal to 2. So the value would be 2 and minus 2. So f of 2 is 2. If I put x equal to 2, this is 2 and this is minus 2. So among these two functions, only one of them is bigger, one of them equals the function value. One of them must equal the function value because that is fx is the max of those values. Now when I put 0, both of them are 0. So what happens is that, so if you plug in some x here, so what you do, you plug in x everywhere here and among them try to find the maximum value. There could be 2 or 3 or 4 whatever functional values here whose value is exactly equal to fx, those are maximum values. And those are the points x where more than one function here actually has the maximum. Those are the points where non-differentiability arises. You will soon see an example that will come in later in this discussion. So I will stop the discussion here, and in the next class I will take up the discussion of directional differentiability of a convex function, and we will go to the notions of subgradient. So this will be done in the next class. I think we have given a lot of information in too short a time. So then this will be picked up at 2:15 in the next class, and from here we will see that we will link it up gradually to optimization and move into optimization theory. So that's, we will see how optimization will play a crucially fundamental role, how convexity will play a crucially fundamental role in developing optimality notions even about functions which are not convex. I will tell you that I will teach you some calculus rules by which you can play around and you can get results about non-convex functions also. And then that will show you the true power of convex analysis and the true power of the max function. Fx is equal to max of f1, f2, fn. So that's the key. When the max function, in the max function lies the key to most optimization issues. So that is the key. So, and that is very important. These max functions come pretty often used by economists in taxation theory, for example. So I will stop here. If there is any question, better to have some little bit of discussions if you want, and then we will. Any questions still? Please ask me. So we have some 10 minutes time, we can discuss questions and answers. So we will start with this in the next lecture, because this is now essentially we are getting into the optimization aspects. We have already got on by telling that the function, for a convex function, every local minimum is global. We have already got into optimization aspects. So we are moving into the optimization aspects now. Anyone? Please ask questions, because without asking questions there is no learning. Yeah. It's important because you see, so if you even think in one dimension, suppose I am talking about differentiability over this. So there is an x, and I am just looking at this is say x plus delta and x minus delta, and these points are included. Now I want to talk about differentiability at this point. So I have to move to this point from this direction, I have to move from this direction, right? So here, now when I talk about continuity also, at the end points we always talk about right continuity and left continuity. So that makes sense. The continuity is not that imposing thing. But now when you talk about the derivative, when you say that I want to come to x from the other side, the function may not be defined here. The function may not be defined here. So however small neighborhood you take here. So suppose you take a small neighborhood around this point. So this is the interval, say I have just created around a point x, or if you want to just look at it like this. So you take the interval AB and you closed interval and you want to look at the differentiability at B. So you take a very small interval. So B minus delta and B plus delta. Intervals are always open intervals. Neighborhoods are always open intervals. Now you see, if I want to talk about the function value here, I just do not know the function value here. I only know the function value here. So derivative as a sense, derivative as a complete sense does not exist. Maybe, for example, one might say, okay, maybe the function is defined over the whole R, and I am just looking at the function in AB, okay? Maybe it's like this. Now you see, this function is very nice, but at B, if you look at it as a function from R to R, at B the function is not differentiable. It has the kink. So if you say that it is differentiable at B, it will have no, you cannot, you won't make sense. So that is why you just have to bother about any, so, but you take any point here, doesn't matter. However near it is to A, you can always have a small neighborhood around it, in which you can look at both sides. That is, you can approach from this side, left side and right side. That is why open intervals are. Now if you ask me about Taylor's theorem, for example, when you do. Taylor's theorem, what you do, when you say that the derivative exists up to order n in the closed interval AB and are continuous, it simply means that when I am coming to the endpoints, the derivative values that I am computing, just derivative computed as a function, the derivatives that I am computing are the left derivative and the right derivative. So right derivative when I am computing at A, left derivative when I am computing at B. So a functional value, the derivative is also a function of x. So f dash x or f double dash x, with f double dash x at all points in the open interval AB, and at the end points I am taking the right interval, right derivative and the left derivative. For f dash b I am taking the right derivative, f dash minus b and f dash plus a, the right derivative for a. So that builds up the function. So there we are looking at, and it is continuous and is assumed to be continuous over the closed interval AB. So that builds up the function. So there is a very crux in, when you in Taylor's theorem they don't write also in books very clearly, this is a crux. The only book that writes it is due to Sam Goldberg. Goldberg writes it absolutely clearly what one means by this statement. Because if people just rectify this statement, they don't realize what they are trying to talk about. So at the end points you are just, see now you are looking at, you are telling that the function, that Taylor's theorem exists, where the derivative exists up to order n and are continuous in AB. So derivative exists, then they are functions of x. So as functions of x they are continuous in the closed interval AB, which means because for functions of x at the closed intervals at the end points I am only bothered with right and left continuity. Okay. So if I am just bothered with that, that is the definition of a continuity over a closed interval. It is continuous over the interval, and at the two endpoints it is right continuous or left continuous. So when I am talking about the derivative values at the right and left endpoints are the right and left derivative. Once you take those right and left derivative and remaining the standard derivative values, that makes up the function. So f double dash x means f double dash right derivative at A, f double dash x for any other x other than B, and f double dash minus b means the left derivative at b. That is the structure of the function f double dash x that you are telling is continuous in the closed interval AB. So these are very subtle things which are ignored. I don't know why, because here the job is to pass the examination and teach others how to pass the examination. So there is a lot of subtlety in analysis, and so one has to be slightly careful.